Alright, so in this video we are going to cover the while command. And while is just that. It's going to do something over and over again until something is satisfied, some condition is satisfied. So for example, let's say we said a number is equal to, let's say awesome is equal to 1, and while awesome is less than or equal to 10, do whatever this is. And so in this case, awesome will equal to awesome plus 1. It's kind of a silly thing to do, but this is just kind of illustrate what while command does. And so now, if I copy and paste this, do that, it's going to keep going over and over again until awesome equals, until this is no longer true, and then it stops doing that. I think you can get a sense of what can happen horribly if awesome was always going to be less than 10. So in this case, if I say awesome is equal to 1, less than or equal to 10, and awesome just equals awesome forever and ever, it's just going to go over and over and over and over again ad infinitum. You see this little thing going blah, 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 blah. That is a problem. So you can actually, if this ever happens to you, just Control C, cancel it and cut the loop, because that will happen if you play with while loops. Eventually you may have something that goes on infinitely, so you don't want that. But then the question is, what can you do with this? Why do you care about the while loop? Well, in this case, the easiest thing to think about is iterative solutions. So if you're going to do something iteratively, you could make the computer do it for you until some condition is met. So I'm going to give this as an example of solving the Newton method for convergence to find a solution of a function. So in this case, I'm going to say the function is equal to, I don't know, what should we say? Let's say f of x is equal to, what would be a good number? Let's say x cubed minus cosine x plus 20, or 20. Yeah, that sounds good. Let's do that. All right, let's not say cosine x. Let's say 5 times cosine x. Okay, so let's say it's that's our function now. Okay, so if we want to find the solution to that function, or a solution to that function, where x is going to equal to 0, let's go with a while loop. So we're going to have to do the Newton method, or Epson method, where you say x new is going to equal to x old minus f of x divided by f prime of x. Okay, so in this function here, I'm going to say f prime of x, I'm going to have to do a quick derivative, is 3x squared plus 5 sine x, and that's it, right? Okay, so that should be the function. So we have our function that we can create. So what am I going to say that we should do? Now the important point here is, and I'm going to intentionally make a mistake, but just so you can see what's going to happen, I'm going to create a delta, meaning the difference between x old and x new. If the x old minus x new is less than or equal to some set value, then I'm going to consider it's close enough, and then we're going to stop. So while x new, let's say the delta is greater than or equal to 0.01. I'm going to say 0.01 is our precision in this case. I'm going to do the Newton method. So what is the Newton method? Well, it's going to be x new, or x new, is equal to x old minus f of x, which is it's going to have to be x old. I'm just going to call it x old x, because that's going to make my math easier. X minus x cubed minus 5 times cosine x plus 20 dot divided by then all the f prime, which is 3 dot times x squared. I don't need the dots, but I'm just putting in there for the sake of argument. Sine dot sine of x. That looks good. Okay, there you go. I think that's enough of the parentheses. There you go. Excellent. So that's our loop. Now I'm going to say x, our delta is going to equal to x minus x new. All right, and that's actually an interesting point here. So I'm going to want the absolute value of this. So can we do absolute value? Help ABS, I think. Yep, absolute value is ABS. So I want the delta, which is going to be the absolute value between these two values. I don't care which order it goes. And I'm going to then say x is equal to x new. Why am I doing that? Well, the thought here then is it's going to loop. So it's going to calculate an x new from whatever x is. It's going to find the difference between x old and x new. And then I'm going to define a new x based on the x new, and then plug that into the GAN until this delta goes below 0.01. Now clearly there's a couple of things here. Since delta doesn't exist, it's going to get mad, so I have to define a delta to begin with. I'm going to say delta starts with 10 just because it's greater than that value. It doesn't really matter. But then I have to have my initial guess of what x is, and that's going to go outside this loop. In this time I'm going to say x is equal to 1 as my initial guess. Great. So I can copy all of this, say run, and if you can see here, it intentionally had a delta value and it's going down and keeps on going until it converges. And you can see x is equal to negative 2.9192. Does that actually satisfy the expression? Let's find out. So if I take this whole thing here, that is what x is equal to. This should equal to close to 0. And there you go. We got the answer. And that's exactly how you can use a do-while loop to link it with the Newton-Raphson method and solve complex values. And this just gives you a chance to do this in a way that's quite simple. I could improve the precision by adding a 0 to this. So if I recreated this entire thing and redid it, then we now have a delta that's much, much smaller. I have an x that is I have a new x that has a higher precision. Plug that in, and we'll get a much smaller value of our a much smaller value closer to 0, which satisfies this expression. So this works out really well. If we tried a different value of 10, would it still converge? And oops. And what happened? Let's see, did that work? X. Oops. Somehow. Let's go back. Go here. Control C. Enter. And there we go. We got the deltas going down. And X is still converging to the same answer that we had before. So this is exactly the function or the power behind the while loop. It allows you to repeat structures and converge as needed if that's something that needs to happen. You can also use it as error check. So, for example, if you go back to the example of a log input, I can actually say while x is less than or equal to -1, or less than equal or is less than or equal to 0, I could say do the following. In this case, input please enter in appropriate x for log. Please enter in appropriate positive value. So this I'm going to revisit our log example. End. And so x is equal to. So here I could say input, please enter a value to of x to find the natural log of. So we can have our first input, and it can do this loop, and it'll take what x is, which is that initial input. It's going to see that input is appropriate or inappropriate, and loop it around and keep on doing this until finally a positive value happens, and then we can say y is equal to log of x. So if I take this entire code, copy and paste it in, please enter a value of log for find a natural log. If I say -5, it says please appropriate positive value, -5, -5, -5, -5, oh, or 5 actually, because I put it 0.5, it gives an answer. So you can get a sense of other ways you can use the while loop as an error check or a iterative check. Obviously this was not a great code because I should put space there, put space here, there you go, and that'll probably be a little bit cleaner, but you can say 0, 0, 0, 0, 0, 0, and you'll see it'll keep on doing that until finally you enter a null value, and interestingly enough, null is still null, so it won't give you any answer. And that's it. So that is, in a nutshell, the power behind the while loop.